Let us solve some problems on capacitor filter circuits, which includes both half wave and full wave rectifier circuits. The first question. In the rectifier circuit shown below, what should be the minimum peak inverse voltage rating of the diode, PIV rating of the diode? You see here only the transformer is given this way. So by default what you take, the turns ratio is 1:1. If that is the case, the RMS value of the secondary voltage is also equal to 12 volts. Then what about the peak voltage? V peak secondary, it is just nothing but RMS multiplied with √2. Okay, it is also fine. Then they are asking us PIV rating now. So what about VD equation? VD is equal to Vm sin theta minus Vm. So PIV is equal to 2 Vm, 2 into 12 √2 volts. It is 24 √2 volts. So option D is correct. Next one. The figure shows a half wave rectifier with a 475 microfarad filter capacitor. The load draws a constant current I0 of 1 ampere from the rectifier. The figure also shows the input voltage Vi, output voltage Vc, and the peak to peak voltage ripple mu on Vc. The input voltage Vi is a triangular wave with an amplitude of 10 volts and a period of 1 millisecond. The value of ripple mu in volts is. See here in this particular example, if you observe, so input is a triangular wave, this one, it is a triangular wave. Output voltage across the capacitor, it is like a triangular wave, charging, discharging, etc. And the peak to peak ripple voltage, this peak to peak ripple voltage is mu. What is that value they are asking? What is the value of this mu? Okay, here we are well aware that VR, peak to peak ripple voltage, it is equal to IDC into T by C. Here IDC is equal to I0 or IL, it is 1 ampere into period 1 millisecond by capacitor 475 microfarad. The answer will be 2.1 volts. It is a straightforward formula based question. We need not worry about whether the input is a sine wave or triangular wave. Output is almost like a triangular wave, charging and discharging of the capacitor, and the peak to peak ripple, peak to peak output amplitude height, right? Peak to peak difference, that peak to peak value, it is just nothing but our ripple amplitude, peak to peak ripple amplitude. The figure shows a half wave rectifier. The diode D is ideal. The average steady state current in amperes through the diode is approximately ID average. We have already gone through all those equations, ID, IL, and current through the capacitor. Let me write I suffix D. So ID average, it is just nothing but IL or IDC. IL is equal to Vm by RL. Vm is equal to 10, RL is equal to 100, its value is equal to 0.1 ampere. So in amperes, it is 0.1. It is also just a formula based question. Next, for the circuit shown in figure, diode cut-in voltage is 0.7 volts V gamma, and the ripple voltage is to be not more than 4 volts. The minimum load resistance that can be connected to the output is, what is the value of RL? Okay, see Vm peak amplitude is 75 volts, which is very much large in comparison with V gamma. So we need not worry about that difference. So what generally we take is output maximum is equal to Vm minus V gamma, it is the exact formula, exact value. But as Vm is 75 and V gamma is 0.7, it is approximately equal to Vm. Okay, in the previous class, previous lecture, in the analysis, I forgot to tell you this point. Okay, if the maximum, we deal with the case where the peak amplitude of the output is input wave is high or output is also high. That's why we neglect V gamma. Okay, so output maximum means Vm we take, that is equal to 75 volts. Okay, then peak to peak ripple height it is given. So we know the formula, peak to peak ripple height is equal to Vm by FRL into C. Vr is known, Vm is known, F frequency is also known, that is 60 Hz, and capacitor is 50 microfarad. So RL is equal to Vm by Vr into F into C. Vm, its value is 75 by Vr4, F is equal to 60, capacitor is 50 microfarad. Okay, so 15 fours, 15 fives, 5 tens. 1 by 16 into 10 power minus 5. 1 by 16 means it comes to be around 6.25 kilo ohms. Okay, 1 by 4 means 0.25. Again 1 by 4, one more 1 by 4 means it comes to be 6.25 something. Right. So option A is correct. In the figure, the ideal moving iron voltmeter M will read. Moving iron voltmeter, it is an AC meter which gives RMS value. Okay, so here what is VD? VD is given by 10 sin omega t minus 10. We are well aware of it. Then what about its RMS value? It is equal to Vm by root 2 whole square plus VDC square. It is further written like 100 plus 300 by 2. Sorry, 100 plus 200 by 2 root 150. So root of 150, how much do you get? It is 12 point something. 12 12s are 144, no? So definitely 12.24. Okay, like this we can write it. I'm not using calculator. I try to avoid using it as much as possible. If not, definitely. The input to full wave rectifier in figure is 240 sin 2 pi into 60t volts. The diode cut-in voltage V gamma is equal to 0.7 volts. If the output voltage cannot drop below 100 volts, the required value of the capacitor is. Okay. So here V input means the primary voltage is having a peak amplitude of 240 volts. And it is 1-to-1 transformer means here across the secondary winding also it is 240 volts. If that is the case, Vs will be equal to one end of the winding to the center tap, it is 120 sin omega t, and other end of the winding to the center tap, it is also equal to 120 sin omega t. Okay. So output maximum, if that is the case, and again here also V secondary, its peak amplitude is 120 volts, which is extremely high compared to V gamma, and hence V output maximum is equal to Vm minus V gamma, which is approximately equal to Vm, that is 120 volts. And what about V output minimum? Output should not fall below 100 volts. Okay, capacitor voltage we know the output voltage waveform. It looks like a triangular wave in which output maximum is 120 volts and output minimum is 100 volts. Then VR, peak to peak ripple voltage, is equal to output maximum minus output minimum. It is equal to 120 minus 100, it is 20 volts. Okay, it is fine. Also, we know that VR is equal to Vm or V output maximum by 2FRL into C. Okay. So, C is equal to Vm by Vr into 2F into RL. Vm is equal to 120 by Vr is 22 into F is equal to 60 into RL 2.5K. So here 120, here 120 we can cancel, and 20 into 2.5, it is 50. So 1 by 50 or 1 by 5 into 10 power minus 4, 1 by 5 means 0.2, it is equal to 20 microfarad. Okay, 20.6 means they might have taken V gamma into consideration, nothing else. If you take V gamma into consideration, right, means V output maximum is equal to Vm minus V gamma. Anyway, V output maximum is equal to, instead of 120, it is 119.3, and output maximum is equal to Vm, right. What I mean to say here is, here output maximum is equal to Vm minus Vr. It is 120, sorry, Vm minus V gamma here. (119.3 volts), so that Vr peak to peak is equal to 119.3 minus 100, it is equal to 19.3 volts. So Vr is equal to V output maximum by 2FRL into C. So C is equal to output maximum 119.3 by Vr, 19.3 into 2 into F is 60 into RL, it is 2.5 kilo ohms. Then you may get some 20.6 microfarad. That is the only difference. Anyway, instead of breaking our head with all these calculations, right, it's an objective type question. No? We can write using this approximation, which is much easier. Without using calculator, you can finish the calculations. Okay, that's it. Next, the peak value of the output voltage V0 across the capacitor shown in the figure for a 232/9 transformer and a 230 volts 50 Hz input, assuming 0.7 diode drop, 0.7 volts diode drop, and an ideal transformer is. Okay, the peak value of the output voltage across the capacitor. What is V output maximum? Okay, here it is a 230 volts and turn ratio is 230/9. So here it is 9 volts. It is the RMS value. So what about V output peak? It is equal to Vm. It is 9 volts. It is less. So definitely we cannot neglect V gamma. Okay, no doubt about it. So V output peak is equal to V secondary peak minus, here in one stage 2 diodes will be conducting, and hence 2 times V gamma. It is center-tapped rectifier, means in one stage 1 diode only will conduct, but here 2 diodes will conduct, so 2 times V gamma we should write. Okay, and we have done the analysis for ideal diodes, but if V gamma is given, what to do? This is what you have to see. What is V secondary peak? So V secondary peak, it is equal to 9√2. Okay, V secondary RMS is 9 volts and peak value is 9√2. 9 root 2 minus 2 into V gamma, it is 0.7. So how much do we get? $11.33. That is the answer. You see, here again the students may think like V output here, V output peak is equal to V secondary peak. If that is the case, 9 root 2, if you take it so, okay, how much do you get? 12.73, which is also appearing as one of the answers, but it is absolutely wrong. Your answer should be 11.33. We should be very careful here. It is not given like right. If it is given like 230 is to, okay, 2 or 3 like that, turns ratio is less. Okay, the primary winding to secondary winding turns ratio is less, than that is a different story, but here it is more, right? So you can't take ideal case. You should take here V gamma into consideration. That is a bridge type rectifier, 2 diodes. The diode drop is really appreciable value. The secondary transformer voltage of the rectifier circuit shown in figure is Vs is equal to 60 sine 2 pi into 60t volts. Each diode has a cut-in voltage of V gamma is equal to 0.6 volts. The ripple voltage is to be not more than 2 volts. The value of the filter capacitor will be a similar problem we did. Okay, so here it is a 60, so we can neglect V gamma, right? Anyway, let us do both the calculations and we can check the things. So first I am taking the ideal case. So V output maximum is equal to V secondary maximum, that is 60 volts, and V ripple factor or V gamma, right, peak to peak ripple is equal to Vm by 2FRL into C. So C is equal to Vm by Vr into 2F into RL. Vm, it is a 60 by Vr 2 volts, 2 into F is a 60 into RL is equal to 10 kilo ohm. 60 cancel, 1 by 4 means 0.25 into 10 power minus 4. So 25 microfarad. So definitely your answer might be 24.4. That is the only close to this 25 microfarad. Okay. Alternatively, what we do? Definitely V output maximum is equal to 60 minus 1.2. Bridge type rectifier now it is. So alternatively, what we can write? V output maximum is equal to Vs maximum minus 2 into V gamma. It is 60 minus 2 into 0.6. 58.8 volts, and Vr is equal to, again now I can write this capacitor value. It is V output maximum by Vr into 2 into F into RL. 58.8 by slightly less than. So instead of 60 we are having 58.8. Accordingly we can see. Definitely it may be, you can just check it. I am not doing it, I am rightly writing the answer. Okay, this is the idea. So if you use this method, we can save the time like anything. Next, in the circuit shown, the input Vi is a sinusoidal AC voltage having an RMS value of 230 volts plus or minus 20%. The worst case peak inverse voltage seen across any diode is rounded up to 2 decimal places. Okay, so what about your secondary voltage? It is RMS value, no? Okay, so two things we can take. One possible value Vs or V secondary maximum or Vm maximum. Let me take maximum as Vm1 or V secondary Vs maximum or Vm maximum. Its value is equal to 230 root 2, because here what is given, it is the RMS value, we are well aware of it. So it is 230 root 2 plus 20% of its value. What I am doing, 230 plus 230 into 0.2 root 2. This is much better. Okay, so 276 root 2. It is 46 means 276 root 2 Vm1. So how much do we get? .390 volts. This is one possible value, which is our PIV 1, I can say. Peak inverse voltage is Vm. Okay, here. And what about the other case? It is equal to, right, Vm minimum I can take. So 230 minus 20%, 230 into 0.2 multiplied with root 2. So how much do we get? 230, 184 root 2. Okay, 230 minus 46. .184 root 2. So 184 root 2. It is 260. 260.2. So this is another possible value. Up to 2 decimal places. Anyway, 390.3 or 260.2. Anything we can take. That's it. Because the worst case peak inverse voltage is seen across the diode. Okay, as it is given, plus or minus, we can look at these two values. In the circuit shown, Vs is a 10 volts square wave of period t is equal to 4 milliseconds with R is equal to 500 ohms and C is equal to 10 microfarad. The capacitor is initially uncharged and the diode is assumed to be ideal. The voltage across the capacitor Vc at 3 milliseconds is equal to, okay, rounded off to 1 decimal place. Okay, it's a very simple question actually. Here over the interval 0 to t by 2 the diode is on and t by 2 to capital T diode is off. What is t? Here 4 milliseconds. So definitely as it is 4 milliseconds, it will be 2 milliseconds. 0 to 2 milliseconds the diode is on because input is a positive going cycle. So 0 less than t less than 2 milliseconds diode is on. Once the diode is on, what is our equivalent circuit? Diode acts as short circuit and it looks like a simple RC network. R is equal to 500 ohms and the capacitor is 10 microfarad. 500 ohms or 0.5K and 10 microfarad. So the time constant here, it is equal to 5 millisecond. During this time the input is, if I take the input, it is like 10 volts, 0 to 2 milliseconds. As it is 10 volts and assuming 0 initial conditions as they mentioned, the capacitor will rapidly charge towards 10 volts with a time constant 5 milliseconds. Okay, and at t, after t is equal to, this will take place up to 2 milliseconds, and 2 to 4 milliseconds the diode will be off. Okay, we'll see during this time interval V output or V capacitor is equal to V final plus V initial minus V final into e power minus t by tau or tau c, anything we can take. Capacitor is charging. So what is V initial? Initial conditions, 0 initial conditions, and V final, if you allow the capacitor to charge completely, V capacitor as t tends to infinite, its value is equal to 10 volts. Time constant is anyway 5 milliseconds. So it is 10 plus 0 minus 10 into e power minus t by 5 milliseconds. Not an issue. And at t is equal to, it is 10 into 1 minus e power minus t by 5 milli. At t is equal to 2 milliseconds, V output is equal to 10 into 1 minus e power minus 2 by 5, 2 milliseconds by 5 milliseconds, 2 by 5, it is 0.4, milli and milli cancel. Okay, and if you calculate it, its value is found to be 3.3 volts. I am directly writing the answer. E power minus 0.4, its value is 0.453, I think so. 1 minus 0.453, 1 minus 0.45, it is 5. Okay. Oh, 5.47 you will get. It's not 3.3. Okay. This is what we can see at the end of 2 milliseconds. And from 2 milliseconds to 4 milliseconds, the next half cycle, 2 to 4 milliseconds, input is a negative going cycle. So definitely the diode is off. 2 to 4 milliseconds. Diode is off. Once the diode is off, there is no path for the capacitor to discharge. It is minus 10 volts. So the capacitor can neither charge nor discharge. It holds the voltage it has acquired. That is 5.4. It is 0.67 only. Sorry friends. There is small correction here. 1 minus 0.67, that is 3. So finally, anyway, we get here 3.3. What I wrote initially is correct. Okay, 3.3. Sorry. So it is 3.3. So the same voltage it maintains from 2 milliseconds to 4 milliseconds. So what they are asking, so diode is off and V capacitor or V output remains as 3.3 volts. Okay. This is what we can observe. Next, if you further extend it from 4 to 6, means again next positive cycle, the diode will be again on. So here, if I take from 4 to 6 milliseconds, during this interval, again the diode conducts and the capacitor continues to charge towards 10 volts from 3.3 volts. Such thing is not required, but our answer here is 3.3 volts. With that, our answer is done. Okay, so if you further want to write the output from, because okay, here I can write V output at t is equal to 3 milliseconds, it is equal to 3.3 volts. Suppose at 6 milliseconds or at 5 milliseconds you want, then what to do? 4 milliseconds less than t less than 2 milliseconds. If you take it so, again V output or V capacitor, it is equal to V final plus V initial minus V final into e power t minus 4 millisecond by tau c. Here what is V initial? It is voltage across the capacitor at t is equal to 4 milliseconds. Its value is 3.3 volts. And what about V final? V capacitor as t tends to infinity, its value is equal to 10 volts. Time constant is anyway known. So V output is now given by 10 plus 3.3 minus 10 into e power minus of t minus 4 milliseconds by the time constant is 5 millisecond. Now at t is equal to, sorry, it is 4 to 6 milliseconds, sorry friends, 4 to 6. So at t is equal to 6 milliseconds, V output is equal to 10 minus 3.3 minus 10, it is 6.7 into e power 6 minus 4, 2. So minus 2 by 5, it is again minus 0.4. Its value is 0.67. Anyway, further if you do the calculations, then you will get it now around 5.5 volt. Okay, you can just check the calculations like this. So this is how we can proceed. Okay, every cycle we can make the calculations. So if you observe the overall response of the system, just these are all additional things. It's not like simply solving the problem and leaving it. Out of curiosity we are doing this. Output voltage, it is 10, 0. Input may be having like this, but here first cycle the output, right, it is charging up to 3.3 volts. Next 2 to 4 milliseconds it remains constant. Next again it is charging up to 5.5 volt. Next it remains constant. Further it will continue to charge like this. This is the idea. 0 to 2 milliseconds, 2 to 4 milliseconds diode is off, 4 to 6 milliseconds diode is on, and 6 to 8 diode is off. Whenever the diode is on, the capacitor continues to, capacitor charges. When the diode is off, the capacitor can neither charge nor discharge, it holds the voltage it has acquired. Right? This is the idea behind this problem. Next, question number 11. Vs is a pulse of 10 volts and duration 5 microseconds as shown in figure 1. Figure 1 means this is figure 1. Okay, and is applied to a circuit shown in figure 2. This is figure 2. Assume that the initial voltage on capacitor is waveform for V output will be, okay, assume that the initial voltage on capacitor is 0. right? Okay, there is some printing mistake, is 0, and the waveform for V output will be, right? And what is the output? That's the question. Okay, how do we do this problem? Okay, see, over the time interval 0 to 5 microseconds, the diode is on, and nothing is mentioned about the diode. We take it as ideal diode, and it acts as short circuit, so that the capacitor tries to charge towards 10 volts. If the time constant is small, rapidly the capacitor will charge. Okay, and it will charge up to a value. So capacitor voltage starts from 0 and it rises to certain level. Okay, no doubt about it. So which means this cannot be possible. Capacitor voltage cannot rise abruptly to 10 volts, and it is not following like this. It is absolutely wrong. We can think of B, C and D. Next point. After 10 milliseconds, after 5 microseconds, the diode is off. Once the diode is off, then what is your equivalent circuit? Like this. So what happens here? The capacitor tries to discharge. Is it possible to say that the capacitor voltage remains constant as the diode is off? Here the capacitor finds a path to discharge. So in the previous problem, the capacitor was unable to discharge when the diode is off. Remember, once the diode is off, here the capacitor can neither charge nor discharge, whereas here once the diode is off, the capacitor discharges, means initially the capacitor will be charging up to 5 microseconds, right? It may charge up to some value, or it may charge up to 10 volts depending upon the time constant. After that, once the diode is off, means after 5 microseconds the capacitor has to discharge. Where can you see that kind of discharge? Here there is no discharge. It is charging up to 10 volts and keeping quiet, so it cannot be the answer. And it is charging up to certain value, okay, 5.47. After that, after 5 microseconds, it has to discharge, which is not happening. So definitely this is also not possible. Without any calculations, I can select D as my option. Let us cross check it. It's not a big deal, right? It looks like a big problem, but nothing is there in this. Just like that, we can conclude the answer. Okay, let us see. Let me check the things. So over the interval 0 to 5 microseconds, diode is off. 0 less than t less than 5 microseconds, diode is on. Once the diode is on, the equivalent circuit is like this. It is 30K and 8K, I think so. And 1000 picofarads means 1 nanofarad I can write for capacitor. And what about Vs or V input? It is equal to 10 volts. Then the capacitor will rapidly charge towards input V 10 volts with a time constant R Thevenin's into C, R equivalent. What is R equivalent here? If Vs is 0, 8K parallel with 30K. So R Thevenin's is equal to 8K into 30K by 38K. It is 120 by 19 kilo ohms. Okay. Then its equivalent circuit is something like this. So the capacitor is rapidly charging towards input with a time constant R Thevenin's into C. It is 120 by 19 kilo ohm into 1 nanofarad. So it is 120 by 19 microseconds. Time constant is small only. Nano, no? Okay. Right. Approximately 120 by 20. Okay. So it is 6 microseconds, approximately 6 microseconds, 6 point something we get. So with that time constant. So if I take V output, it is V final plus V initial minus V final into e power minus t by tau c. V initial, voltage across the capacitor at t is equal to 0 plus, it is with 0 initial conditions, it is 0. V final, it is V capacitor as t tends to infinite, its value is 10 volts. So V output is equal to 10 plus 0 minus 10 into e power minus t by tau c. 10 into 1 minus e power minus t by tau c. At t is equal to 5 microsecond, V output is equal to 10 into 1 minus e power 5 into 10 power minus 6 by 120 by 19 into 10 power minus 6. Micro cancel, 5 24s. So it is a 10 into 1 minus e power 19 by 24. Okay. So how much do you get? It is 5.47 volts. This is voltage across the diode at 5 microseconds. So the capacitor starts charging towards input voltage like this, and it reaches up to 5.47 volts. Done. And for t greater than 5 microseconds, diode will be off, because what happens, the input is falling to 0 volts. By that time, means the input is 0 means anode voltage is 0, the cathode voltage is 5.47, output is 5.47, the diode will be off. Once the diode is off for t greater than 5 microsecond, diode is off. The equivalent circuit now appears this way. It is 20 kilo ohm and it is 1 nanofarad, 5.7 volts. So the capacitor starts discharging through this 20k, sorry 30k, not 20k, 30k. So implies the capacitor starts discharging through 30k with time constant tau d is equal to 30k into 1 nano. It is equal to 30 microsecond. It is large. Discharging time constant is large. So capacitor slowly discharges. So here it is slowly discharging like this. Okay, here the charging time constant is approximately, I am writing 6 microseconds, and the discharging time constant is 30 microseconds. Okay, it may be some 6.1 something. I am writing approximately 6 microseconds. At the end of 5 microseconds, the capacitor will charge up to 5.47 volts. Right? Without all these calculations, right? Without all these calculations, just like that, we can conclude, if we have proper understanding of the circuit. Okay, that's it. These are some of the questions asked in previous papers.